In this video, we will be exploring the Rotational Motion Nanometer Lab by Matthew Chen. Background on rotational motion. Rotational motion, the motion of a point in a circular path where the center point is fixed on the fixed axis of rotation. Rotational motion causes centripetal force, which is the force that holds moving objects in a circle, such as a roller coaster moving in a loop or the Earth orbiting around the Sun. With this rotational motion, the object's rotation is always pointing into the center of the Earth. Testable question. Can the position and setting on a hairdryer affect the rotations per second on an nanometer? Hypothesis. If the distance between the hairdryer and the cups are shortened, then the revolutions per second of the nanometer will increase. Basic lab concept. In this lab, we will be building a homemade nanometer that will measure the rotations per second based off of the force created by the air in the hairdryer. We will do this in 3 different distances away, 2 feet, 3 feet, and 4 feet. This will be done by a 2-speed, low and high powered Con Infinity Pro hairdryer. The concept presented will be focused on rotational motion and the rotations created by the air into the cups on the nanometer. We will be building a homemade nanometer comprised of 4 cups, skateboard wheel and ball bearing as a base, popsicle sticks, hot glue, and a wooden rod. The measurements can be shown on the board, with the diameter of the paper cups being about 3.5 inches and the length of the nanometer being about 15 inches. These are more images of the nanometer that I built utilizing the materials listed before. As you can see, the ball bearing is hot glued to the stick, which is creating the rotational motion part of this lab. The Infinity Pro Conhair hairdryer was utilized in this lab to create the force to push the cups, causing the rotations. This hairdryer is equipped with low and high settings, causing different forces acting on the nanometer. For this lab, the controls are listed as weight, position, and environment. I weighed the nanometer and it came out to be 174 grams. The start position was also a control, with the cup always lining up with the start point at this moment. The environment was also controlled. It was a cool, thermostat controlled environment without any wind affecting the nanometer. The mounted nanometer was mounted to a table utilizing duct tape, and 3 markers were placed 2, 3, and 4 feet away from the nanometer, marking the different distances that we would test. I turned the hairdryer on low and pointed the nanometer while recording at a 10-second period in order to test the rotations per second. I repeated the same process on high, then I moved back from the 2 to the 3 feet away marker and back to the 4, repeating both with low and high heat on the cool setting in order to turn the cups with the air. This is trial 1 of the video. It is 10 seconds long and it is 2 feet away with low speed on the Conair Infinity Pro. As you can see, it was moving at a considerable fast rate of speed, with the ball bearing turning the cups and the force of the Conair Infinity Pro propelling air into the cups, pushing it back, creating a rotational circular motion. This yellow marker with the white piece represents the starting point of the cups. This is trial 6. You can see the cones are lined up with the starting marker. Trial 6 was taken at 4 feet away at high speed. This is the farthest distance we have tested. As you can see, in the 10-second period, it has not moved that far. It has maybe gone half. This is because the Con Infinity Air Pro had a hard time reaching the inside velocity of the cups, pushing it forward. After the 6 trials, the graph displayed here represents the results of the trials. As you can see, the 2 feet with low power had the highest revolutions per second, coming in at around 2. This graph, which is the constant graph, represents the mass versus revolutions per second. The mass in this lab was constant and was controlled at 174 grams. As you can see, the mass was constant throughout the whole entire experiment and was not changed at any point. This is the result of trial 1. As you can see, trial 1 had the highest revolutions per second, coming in at about 2 revolutions per second. This is a revolutions versus seconds graph displayed here. As you can see, we utilized a prior equation in the lab to find the angular frequency. 0.52 represents 1 over frequency simplified, while 6.28 represents 2 pi. To get W by itself, we multiply W onto the side to the left and divide 0.526 onto the side to the right. This results in an angular frequency of 11.94 radian seconds. One possible error for this lab was the blow dryer's angle onto the cups. This may have resulted in less air entering the cups, resulting in a less rotations per second. This may have been due to human error of operating the blow dryer. Concluding statement. In the end, the results showed that when the blow dryer was closer to the nanometer, the revolutions per second was higher than when the blow dryer was farther away. Displayed through the video, it was clear that with the 2 feet low speed that was going about 2 rotations per second was much faster than the rotations of the 4 feet high speed, which was barely going 0.5. This turned out to prove my hypothesis correct, that with lower distance equals more revolutions per second. Future changes. An interesting change I would like to bring to this lab would be to change the hair dryer for something more powerful such as a leaf blower.